All right, so in our class meeting on Tuesday, we looked at the concept of complex power and came up with the following relations. So let's just call this complex power very brief. So we plotted our complex power for a given load on a complex plane. Here is our real axis. Here is our imaginary axis. Let's call our complex power S here. Do it in purple. We found that the projection of S onto the real axis was our average power. The projection of S onto the imaginary axis was our reactive power. The length of this vector was our apparent power. And we had this guy right here, which we called our power factor angle. These relationships can be summarized mathematically as S is equal to the RMS phasor voltage times the complex conjugate of the RMS phasor current, which in rectangular form looks like P plus JQ. And in polar form, this looks like apparent power angle, power factor angle. Well, today we're going to kick, oh, sorry. Thank you, Christian and Ethan, and other people typing here. Thanks. So today we're going to be focusing on the concept of power factor. Okay. All this stuff in chat is just people saying that they're here. So now let's get into the nitty-gritty, what the power factor is, what it tells us. So the power factor at which an electrical element or network operates at is a measure of the efficiency of power transmission to or from the network. Mathematically, our power factor PF is defined as the ratio of the average power to the apparent power, which comes out to be simply the cosine of theta S. From this, power factor values range from -1, meaning that our network is supplying apparent power at 100% efficiency, to +1, meaning our network is absorbing apparent power at 100% efficiency. Whenever a load operates at a power factor that is less than 1 in magnitude, it means that the source is being required to generate more than the minimum volt amperes necessary to supply the required average power needs of the load. What this means typically is that the expense to the supplier of the power is higher as more energy needs to be generated, and the load and transmission system will see higher currents, which require a more expensive infrastructure to safely maintain. So let me recap that long-winded thing with something that's pretty straightforward here, okay? Average power is what we as consumers buy or pay for whenever we pay our electricity bill. Apparent power is what electric utilities pay to produce. I say they pay to produce that because they may have to buy coal to burn, to run their steam turbines and all that kind of stuff, which generates electricity for the grid. Or they may have to buy, accept the cost of installing a hydroelectric plant or something like that. And they also have to pay for apparent power because they have to provide the infrastructure, meaning the cables and all that kind of good stuff that's required to send large amounts of currents at a specified voltage rating, okay? So average power is what we as consumers pay for. Apparent power is what the electric utility provides. And so the power factor is just a ratio of those two quantities, meaning the lower the power factor is, the more expensive it is to operate for the utility. Okay. All right, so in an industrial load, we might see power factors that could be considered low by a industrial supplier. So in our homes, we typically operate loads like computers, televisions, and things like that, that while they run off of AC power, they contain what are called rectifiers, which are effectively converting that AC signal into a DC voltage. And so computers, televisions, and most modern electronic devices only consume average power. It's only when we get into appliances like microwaves and fans and washers and dryers and things like that, that we start to see any type of reactive load on our system. But as a whole, for a home use, we should expect our power factor to be very, very close to 1. Now let's contrast that with an industrial setting, like a manufacturing plant that may have several induction motors that are controlling various processes like running conveyor belts and things like that. We might see that the power factor at an industrial or commercial place might be in the ballpark of 0.7, 0.6, 0.8, somewhere in there, meaning that they're operating at a very low efficiency. This costs the electric utility money. And so typically speaking, they find places where the power factor isn't at least 0.95 or higher. Industrial consumers can avoid this find by employing a technique called power factor correction, which is the last topic that we're going to talk about today, and it's the last topic that's covered in this class. Okay, so I'm just setting us up for what we're going to be talking about in a little bit. But now let's get back to concept of power factor in a more general sense. Okay, so the power factor is combined of actually 2 pieces of information. We have the magnitude of the power factor, which is given by these mathematical equations, and then we have the power factor as either leading or lagging. And whether the power factor is leading or lagging depends on the sign of the power factor angle, theta s. So when 0 is less than theta s is less than 180 degrees, we have a lagging power factor. And that simply means that the current is lagging the voltage, which indicates that we have an inductive load. When negative 180 degrees is less than theta s is less than 0, so effectively if our power factor angle theta s is negative, we have a leading power factor. So let's work an example here that utilizes these power factor relationships. And this is the type of problem you may see if you went into power engineering. So let's consider a system where we have some RMS phasor voltage source, let's call it Vs. And it is going to be supplying power to 3 industrial loads. And I'm going to put the loads over here. But instead of specifying them by their impedance or something like that, we're going to look at how they would be specified from an industrial standpoint. Let's look at load number 1. And we are told that it is absorbing 30 kilowatts at a power factor of 0.8 leading. We're going to have a second load over here. Call this load number 2. It operates absorbing 20 kilovolt amperes with a power factor of 0.9 lagging. And here's load number 3. Which absorbs 10 kilowatts at a power factor of 0.8 lagging. And we can measure the voltage drop across our 3 industrial loads connected in parallel. And in doing so, we observe that the voltage drop across them is 480 angle 0 degrees volts RMS. And to make this a little bit more tricky, we are going to assume that the transmission lines, nothing more than a fancy word for wires, that connect our source to our 3 industrial loads in parallel, has some impedance that is given by 0.1 plus J 0.2 ohms. And our goal here is to determine the power factor at which the source Vs applies power. Okay. So what we are going to do here is we are going to apply Telogens Theorem, which I talked about on our very second class meeting. Telogens Theorem simply states that the sum of the power absorbed in a system has to equal the sum of the power supplied in a system. And we're going to use that relationship to say that Vs, the complex power that is supplied by our voltage source, is going to be the sum of SW, the complex power absorbed by our transmission lines, plus S1, the complex power absorbed by load 1, plus S2, the complex power absorbed by load 2, plus S3, the complex power absorbed by load 3. So effectively, we're going to see all three of our loads absorb some power, and then because our transmission line has a impedance that is non-zero, it is also going to absorb some, hopefully, very small amount of complex power as well. We're going to determine these four things that contribute to the power that's supplied by our source by using our definition for the power factor, right? So our power factor mathematical definition is simply average power over apparent power, or the cosine of theta s. So let's start by determining S1. So for load 1, we are given two very critical pieces of information, okay? We are told that it is absorbing 30 kilowatts, and we are told that it operates at a power factor of 0.8 leading. These are the only two pieces of information that we need to know in order to determine the complex power that is absorbed by this load. So the first thing that we need to figure out is the 30 kilowatts of power that's absorbed by this load. Does that represent average power, reactive power, or apparent power? Do any of you guys have any thoughts on that? So Devarier has suggested that the unit of apparent power is the watt. Unfortunately, he is mistaken. Average power is measured in watts, reactive power is measured in VARs, and apparent power is measured in volt amperes. Since this load is absorbing 30 kilowatts, that tells us that 30 kilowatts is the average power. So what we can do is say that the average power absorbed by load 1 is going to be the apparent power absorbed by load 1 with an angle that I'm going to call theta 1. The apparent power absorbed by load 1 is simply going to be the average power absorbed by load 1 divided by the power factor at which load 1 operates, which I got simply by manipulating this expression right here. Our angle, theta 1, is going to be the inverse cosine or the arc cosine of our power factor, but we need to pay attention. So we are told that the power factor for load number 1 is leading, which means that we need to have a negative phase angle. The inverse cosine function will always give us a positive phase angle. So to fix this, we just put a negative sign out front here. So if I put in my numbers, what I get is 30 kilowatts divided by 0.8 with an angle of negative inverse cosine of 0.8, and this comes out to be 37.5 angle negative 36.870 degrees kilovolt amperes, because we're dealing with complex power now. We can do something similar to determine the complex power absorbed by load 2. So S2 will also be simply the apparent power absorbed by load 2 with an angle of the power factor angle of load 2. If we look up here, we're told that load 2 is absorbing 20 kilovolt amperes of power. Does this 20 kilovolt amperes represent average power, reactive power, or apparent power? So you guys have got it mixed up yet again. The watt is the unit of average power, and the volt ampere is the unit of apparent power. Yeah. So since we're told that it's absorbing 20 kilovolt amperes, we already know what our apparent power is. It's literally just 20 kVA. And then our angle is going to be the inverse cosine of our power factor, which in this case is 0.9. And because our power factor is described as lagging, our angle has to have a positive sign. So if we throw this into our calculator, what we get is 20 angle 25.842 degrees kilovolt amperes. So these calculations that we just did were very, very similar. Sarah, to double check, watt is average power, volt ampere is apparent power, and volt ampere reactive, or VAR, is the unit for reactive power. So as I was saying a moment ago, the calculations that we just did here are extraordinarily similar, but distinctly different. And in the ways that they are different, sorry, let me answer this question. So Devarier asked, were those angles in radians when you typed it in the calculator? I'm not typing an angle in the calculator at all. I'm typing a ratio into the calculator. So the inverse cosine, the argument of the inverse cosine function is going to be a number that is between -1 and +1. And then when I do the inverse cosine function in my calculator, it's going to spit out an angle in degrees if I tell it if it's in degree mode, or it's going to spit out an angle that is in radians if it's in radian mode, right? So just to double check things here, I'm gonna, well, I thought I was gonna grab a calculator, but I apparently don't have one on me. Okay, all right. Okay, so coming back around here, sorry. The critical pieces of information that we need to pay attention to when doing this type of calculation is the unit on the power and whether the power factor is leading or lagging. If we are given average power, meaning watts, or reactive power, meaning VARs, we will have to divide that number by our, well, actually, if we're given average power, let's only say average power, we're going to have to divide that number by our power factor in order to get apparent power. Okay. If we are given units of volt amperes, we do not need to divide by the power factor because we already have the apparent power. And if we are told that our power factor is leading, we need to include a negative sign when we do our angle calculation. If we are told that the power factor is lagging, we do not need to include the negative sign. Okay, so these are small little things that if you miss them, you'll wind up getting the wrong answer. All right, so let's talk about load 3. So this is going to be simply the apparent power of load 3 with an angle of the power factor angle of load 3. So one of you guys tell me what the apparent power is supposed to be. (10 over 0.8). That is exactly correct. And that comes out to be 12.5. All right, scroll back up here. Now you guys tell me what the angle is supposed to be. Is it going to be negative inverse cosine of 0.8 or positive inverse cosine of 0.8? So it's going to be positive inverse cosine because we have a lagging power factor. Okay. Anytime the power factor is lagging, our phase angle is positive. Anytime our power factor angle is leading, our power factor angle will be negative. Okay, so lagging means negative angle, excuse me, lagging means positive angle, leading means negative angle. So we're going to have inverse cosine of 0.8. And that's going to look like positive 36.870 degrees kilovolt amperes. So we have determined the complex power absorbed by load 1, load 2, and load number 3. Do I need to talk about how we got these values anymore? Is anything still confusing? All right. Nobody is saying things are let's see what chat says. No, great. Thank you, Sarah. So we have effectively checked this bit, and this bit off our list of stuff to solve for. okay? Our last thing then is the complex power absorbed by our wire. Okay. Now we are given the impedance of this wire, which means if we can determine either the voltage drop across the wire or the current flowing through our wire as an RMS phasor, if we can get either of those pieces of information, we can determine the quantity SW. Which of those two pieces of information do you think we can solve for based on the information that we currently know? The current, absolutely right, Devarier. So there are two different ways that we can solve for that current. Okay. They're both effectively the exact same thing, but it's really just kind of the order of the steps that we would take, okay? So what I mean by that is we could apply Kirchhoff's current law and we would find that the current flowing through our transmission line would be the sum of the current flowing through load 1, the current flowing through load 2, and the current flowing through load 3. So we could solve for those individual currents by dividing our complex power absorbed by our load by the voltage, and then paying attention to whether or not we need to do a conjugate operation. Or we could lump all three loads together, divide by that voltage, and figure out effectively the total current flowing into the composite load, which will be IW. So effectively, do we want to add the three loads together and solve for the current directly, or do we want to find the three individual currents and then add those currents together to solve for IW? Either way is going to give us the exact same result. We're just doing the combination first or the combination second. It's up to you guys. So are we adding the currents or are we adding the powers? Adding the currents. Okay. So if we're going to add the currents together, that means we're going to need to solve for the individual currents. Okay. So the complex power S1 is given by the voltage drop over load 1 times the complex conjugate of the current flowing through load 1. So this means that the complex conjugate of the current is simply S1 over V1. And what I can do is I can take the complex conjugate of both sides of this, and if I conjugate the conjugate, this is just going to give me the I1 that I'm looking for. Okay. So I1 is going to be the complex conjugate of S1 over the complex conjugate of V1. Because when I conjugate a fraction, I conjugate both the numerator and the denominator. So here is S1 right here. I've underlined it in orange. What is the complex conjugate of S1? What do I need to do to S1 to get the conjugate? So adding or subtracting 180 degrees is the same as multiplying by a factor of -1, which is not the same as the conjugate operation. The conjugate operation involves changing the sign on the imaginary part of, or changing the sign on only the imaginary part of the complex number, not changing the sign of the whole thing. So for a complex number in polar form, that is just simply changing the sign on the angle. So the complex conjugate of 35 angle -36.870 degrees is 37.5. We leave the magnitude alone. Angle positive 36.870 degrees. kVA. And then I'm going to scroll up here. So my voltage is 480 angle 0 degrees. So the conjugate of that is going to be 480 angle, and I'm going to put -0 degrees here, even though 0 and -0 are the same thing, just as a reminder that anytime I see the conjugate operation, I need to change the sign on the phase angle of my complex number. So because this is a different way than I worked this problem out previously, I need to pop upstairs just very quickly and grab a calculator. So give me like 2 minutes. All right, so let's throw this in my calculator, 37.5 with an angle of 36.870 divided by 480. Multiply that by 1,000 to make it in amps versus kiloamps. I get 78.125 with an angle of 36.870 amps RMS. And I'm sorry, I put the wrong units here. This should be volts RMS. Our RMS phasor current I2 will just be the complex conjugate of S2 over that same voltage, because all of those loads are connected in parallel. So here the conjugate of S2 is going to look like 20 angle -25.842 degrees kilovolt amps over 480 angle -0 volts RMS. Putting that in my calculator, negative 25.842. Divided by 480 times 1,000 to get the units right. I get 41.667. Angle negative 25.842 degrees, amps RMS. And looks like I'm going to have to go to another page here. Three is going to be conjugate of S3 over conjugate of V3. So that's going to look like 12.5 angle negative 36.87. Over 480 angle negative 0 degrees, volts RMS. And throwing this into my calculator. I get 26.042. Angle of negative 36.870 degrees amps RMS. Absolutely, Sydney. My computer will let me. And this should be a conjugate sign there. Alrighty. So now that we know these three currents, we can say that IW, the current flowing through my transmission line, is just I1 plus I2 plus I3. If I add those three numbers together, I get 121.540 angle 6.182 degrees. So now what I'm going to do is I'm going to use one of the alternative relationships that we developed at the end of Tuesday's class meeting that will allow me to calculate the complex power absorbed by the wire, only knowing the current through the wire and the impedance of the wire. So I can say that SW is the magnitude of IW squared times ZW, which is going to be, sorry, this should be amps RMS, 121.540 amps RMS squared times 0.1 plus J 0.2 ohms. Sorry, units are important. Which comes out to be 3,303.113 angle 63.435 degrees volt amperes, or 3.303 angle 63.435 degrees kilovolt amperes. So finally, we can say that SVS, the complex power supplied by my voltage source, is SW, the complex power absorbed by my wire, plus S1, the complex power absorbed by load 1, plus S2, the complex power absorbed by load 2, plus S3, the complex power absorbed by load 3. If I add all these numbers together, so that's going to be 3.303 with an angle of 63.435 plus 37.5 with an angle of negative 36.87 plus 20 with an angle of positive 25.842 plus 12.5 with an angle of positive 36.870. Let me make sure I got all the signs on my angles correct. Looks like I did. I get 59.570 with an angle of negative 3.203 degrees kilovolt amperes. The power factor at which the voltage source is supplying power is then the cosine of negative 3.203 degrees which is 0.998 and some change. And this power factor is leading because the angle is negative. So I'm going to give you guys fair warning. On your exam, I'm going to ask you to calculate power factors. And I'm going to give you the correct numerical answer and leading, and the correct numerical answer with lagging as well. The expectation here that you can tell me which one of those is correct, and it is based entirely on the sign of the angle, okay? So if the power factor angle is positive, the power factor is lagging. If the power factor angle is negative, the power factor is leading. All right. Let's wrap things up here by talking about the concept of power factor correction. I need to go back. So it is based on the angle that we get. So let me go back here and I'll try to explain this again. Okay. So we were trying to find, let's scroll up here. We were asked to find the power factor at which our voltage source is supplying power. So we calculated the amount of complex power that our voltage source is supplying. And then we used the angle of that complex power to determine our power factor, okay? Because the angle was negative, we had a leading power factor. Now, if we look up here at some of these intermediate steps that we took, S1 right here, calculating the complex power absorbed by load 1, we put this negative sign right here because we were told that the power factor was leading. When we calculated S2, we put this positive sign right here because we were told that the power factor was lagging. Did that help to clarify things, Devarier? All righty. So now we are going to talk about power factor correction. So let's say that I have an industrial load which has a power triangle that looks something like this. Here's the real axis, here's the imaginary axis, and here is S, and I'm going to call this S old, okay? This represents the complex power that is absorbed by the load before we apply our power factor correction technique. Now, we don't know what this power factor correction technique is just yet. We're going to talk our way through it, figure out. So this complex power forms an angle that I'm going to call theta old with the real axis. Since power factor is defined to be the cosine of theta s, if we want to make our power factor increase, do we need to make theta s larger or smaller? Smaller, absolutely correct. So our goal is that after power factor correction, I'll do this in, I guess, light purple, we might have something like this, where I'm going to call this S new, and I'm going to call this angle theta new, okay? If we've made the angle smaller, then our power factor will have increased, and an increase in power factor, meaning that it is closer to 1, is an improvement, okay? So now let's pick apart a couple of things here. So the projection of, I think I used red earlier, both of our old complex power and our new complex power on the real axis is the average power, which I'm going to call P old. The projection of the old complex power onto the imaginary axis is Q old, and the projection of the new complex power onto the imaginary axis is going to be Q nu. So the question then becomes, what do we need to do to make S old look like S new? Well, effectively, S old is absorbing a lot of reactive power, and S new is absorbing less reactive power, which means in order to perform power factor correction, we must supply some reactive power into our system. Okay. Now, at the end of Tuesday's lecture, we learned that the complex power that is absorbed by an inductor was given by, let me get my notes here just so that I am consistent with what I did the other day. Here we go. So for an inductor, we had the relationships J times V effective squared over omega L. And this was equal to J omega L times I effective squared. So inductors absorb complex power. Okay. So putting an inductor into this system is actually going to cause the power factor to get worse. For a capacitor, we found that SC, the complex power absorbed by a capacitor, was given by negative J omega C times VRMS squared, or negative J times IRMS squared over omega C. So if we put a capacitor into the system, we can actually lower the amount of reactive power that is being absorbed. So I'm going to call this difference right here S cap. Okay. And we can relate S cap, which is just the difference between S old and S new, to the size of the capacitor that's needed to get a specific amount of power factor correction using this equation that I've underlined in green here. Okay. So mathematically, what this process looks like is we have S old is equal to P old plus J Q old. S new is P old plus J Q new, and S cap is S new minus S old. Which is going to look like P old plus JQ new minus P old plus JQ old. P old minus P old cancels out. And so this just leaves us with J Q new minus Q old, or J times Q cap, okay, where Q cap is the amount of complex power that's being absorbed by our capacitor. Now, I want to point something out here. Q cap is always going to be a negative quantity. If we look here, this is also Q cap, because Q cap is just the reactive power or the imaginary part of the complex power. And so if we equate those two relationships, what we find is that C, the value of the capacitor needed to apply power factor correction, is given by negative Q cap over omega multiplied by the effective value of the voltage across the capacitor squared. And this can be written as P old times the tangent of theta old minus the tangent of theta new all over omega times V effective squared. This is the form that I prefer, because the pieces of information that go into the expression are usually a little bit easier to find. So let's work a quick example problem here, and then I'm going to stop talking. Okay. This is, once I upload the practice test, you'll see that this is a pretty representative problem of what I might ask of you. Get that practice test uploaded today. So we have a voltage source that's operating at 400 angle 0 degrees volts RMS at a linear frequency of 50 Hertz. And this is connected to a motor, where the motor draws 1 kilowatt at a power factor of 0.8 lagging. To perform power factor correction, we would simply place some capacitor C in parallel with our voltage source to increase the power factor at which our source is supplying power, or effectively to increase the power factor at which our motor is absorbing power. So our target here is what value of capacitor C must be used to increase the power factor at which the motor absorbs power from 0.8 lagging to 0.975 lagging. Okay. Our equation is C is equal to P old times the tangent of theta old minus the tangent of theta new, all divided by omega times V effective squared. So we are going to break this down into digestible little bits, okay? We need to figure out what P old is. We need to figure out what theta old is. We need to figure out what theta new is. We need to figure out what omega is. And we need to figure out what the effective is. Does anybody have any thoughts on how we might figure out any of those 5 quantities that we plug into our equation? So nobody's saying much of anything. So let's start with something that I think is pretty straightforward. V effective in this case is the voltage drop across the capacitor expressed as an effective voltage or RMS voltage. Since our capacitor is literally in parallel with our voltage source, I believe very strongly that V effective is 400 volts RMS. Okay. So effectively, we're just looking for this thing right here. Whatever the magnitude of the voltage drop across the capacitor is the V effective that we're looking for. So I'm going to come down here and I'm just going to call this 400 volts RMS by inspection. We didn't need to do any work for it whatsoever. The next easiest thing for us to determine is omega. Right here is our linear frequency f, which is simply omega over 2 pi. So we could say that omega, this will erase, is just, this will write now, 2 pi times f, which is 2 pi times 50 hertz, or 100 pi radians per second. So 2 of our 5 pieces of information are known just from looking at our voltage source. Okay, so I feel like that's pretty easy. Now let's get into some slightly more difficult things. Well, theta old is the angle of our complex power prior to power factor correction. It is related to the power factor before we do our power factor correction. So theta old is just going to be the inverse cosine of PF old. And because it's lagging, this is going to get a positive sign. So the inverse cosine of 0.8 is 36.87 degrees, because we've done this, I think, 3 times at this point. So I remembered what that angle is. We can figure out theta nu in effectively the exact same way. That's just going to be the inverse cosine of our new power factor. And since our new power factor is also lagging, this is going to be a positive angle. So we're going to have inverse cosine of 0.975, which is 12.836 degrees. So the only thing that we have left to figure out is P old. Does anybody have any thought about P old? Could anybody tell me what P old represents? So let's go back to our graph. P old is the average power absorbed by our load, both before and after power factor correction. Okay. Sarah, it's not a problem at all. And also, you're not slow. So P old is average power. What is the only thing in this whole problem description that has anything to do with power? The 1 kilowatt. Absolutely correct, Sydney. Now, does the 1 kilowatt represent average power, apparent power, or reactive power based on the units? Average power. So that means P old is just 1 kilowatt. We now have everything that we need to plug into the equation. And if we put those numbers in that we've developed, we would find that C is equal to 10.387 microfarads. So I'm just going to write some little hint type things down here to help you guys recall what these things are. So P old is the average power absorbed by the system before and after power factor correction. Theta old is the at which the load absorbs power before power factor correction. Theta nu is just the angle at which the load absorbs power after power factor correction. omega is just 2 times the linear frequency, which we've talked about that before. And V effective here is just the magnitude of the voltage drop, RMS phasor voltage across the capacitor. The only things that you'll ever actually have to really do any analysis on might be this bit right here and this bit right here. Typically speaking, on the exams though, I literally give it to you. If I don't give you P old directly, I will tell you something like the motor absorbs 8 angle 38 degrees kVA before power factor correction, in which case this would be theta old, and this is the apparent power S old. And once we know S old and theta old, we can figure out power factor and all that kind of stuff. In fact, let me pull up an old test, if you guys will bear with me for 5 minutes or so. Let's see, 221. Let's look at what I did this past fall for exam 1. And I don't have anything saved as a PDF, so I will just have to open it up in Word. Let's scroll all the way to the last problem. Always the last problem I ask because it's the last piece of material we cover in this class. Oh, sorry, this shouldn't be exam 1, it should be exam 3. Sorry. All right. So let's look at the pieces of information that we have here. 600 volts RMS. So that is the effective. Frequency of 60 hertz. So omega is 2 pi times 60 hertz. EF new is given by 0.975 lagging, which means theta new is the inverse cosine of 0.975 lagging. Which is just 12.836. I even used the same number as I did in the example problem here. 0.72 lagging is PF old. which means theta old is the inverse cosine of 0.72, which is 43.946 degrees. And then I give you 8 kVA, so that's the magnitude of S old is 8 kVA. And so from this, P old is just going to be the magnitude of S old times the cosine of theta old, where I'm getting that relationship because I know that power factor is equal to P over the magnitude of S, which is equal to cosine theta S. So apparent power times cosine of theta S gives you average power, which is what we're looking for here. So that is 8 times the cosine, actually, couldn't we just do, since cosine of theta old is power factor, just S old times power factor old gives us P old. So I don't even need to do cosine of anything, just times 0.72. 5.76 kilowatts, and then we would have everything to go into our equation. So again, just showing you this because this is the last thing that we're going to talk about in this class. This is what I expect you to be able to do on your exam. Literally pick apart the little pieces of information that I give you to plug into that one equation. It will be some variation of this exact problem, the things that might change. I might give you average power as opposed to apparent power. The values for the power factors can be different. I might tell you that it's operating at 50 hertz instead of 60 hertz, but effectively the problem is going to look almost exactly like this. And once I post the practice exam here in the next couple of minutes, you will see I am not kidding. So any questions on anything? Devarier, I thought I already had posted it to Moodle, but I will double check that to make sure. And I'll try to get this lecture up tomorrow morning, I think, at the absolute latest. Any other questions? All right, well, nobody's saying anything. So I just want to remind you all that your exams will be available Tuesday, Wednesday, Thursday, and Friday of next week. And I am free on Monday afternoon to answer any questions you might have about any material throughout the entire duration of the course that confuses you. I say that because this last exam is a cumulative exam. It is roughly 30% exam 1 material, 30% exam 2 material, and then 40% new material that starts at op amps and goes all the way through power factor correction, which we covered today. I hope you all had at least a not terrible time taking circuits online with me, and I will see you all later. Josh, I don't think so, because I don't believe your grades are due until later on, but don't quote me on that. Give me just a moment here to actually pull up the academic calendar and make sure I'm not telling you something wrong. definitely don't want you messing, or I don't want me to be the reason you don't graduate. Let's see, LaTeX Academ Calendar Summer 2022. Just a moment, Valeria, and I will happily answer you. So degree candidate grades are due on BOSS by 3:30 p.m. on Monday, August 15th. So Josh, that means you do not have to take your exam early. Answering both your and Valeria's question then. The exam will be available for you all to take on August the 9th, August the 10th, August the 11th, and August the 12th. So Tuesday, Wednesday, Thursday, and Friday, there will be an afternoon version of the exam and an evening version of the exam, just like the other tests. So you just take your test in one of those 8 different options, whatever works with your schedule. And if that doesn't work with your schedule, like it doesn't with Mr. Bird, I will happily put something up for you earlier so that you can take it then. But since the quarter ends on Friday, that's the last day I'm going to allow you to take the test. Any other questions?